Well, let's go ahead and get started. Let's see. Good morning, everyone. So, anyone have any questions on anything before we get started? Or okay, cool. Good. Good talk. Good talk. Good Friday morning. So, let's go ahead and conclude our lecture on optimization. So, before we do, quiz today from today until tomorrow, covering lessons 23, 24, and then quiz 10 on next Friday, covering lessons 25 and 26, and then no class on Wednesday, November 4th, so next Wednesday. So I guess let's go ahead and conclude our journey through optimization. So nothing much new in the way of introductory stuff, so let's just go straight to example 1. So example 1, so a recreational court with area 640,000 square feet is to be built on the side of a gym. So the wall of the gym bounds one side of the court. To minimize costs, it is necessary to construct the fencing using the least amount of material possible. So assuming that the fencing material costs $56 per foot, what is the least amount of money needed to build the fence? And then write your answer to 2 decimal places. Okay. So part A is draw a picture, as we've been doing. So the thing is that we have this recreational court which is to be built on the side of a gym. So here's the side of our gym. So, well, the thing is that we have this recreational court that's to be built on the side of the gym. So essentially we have this rectangular looking object that, if you notice, looks very similar to what we've been doing regarding dealing with garden problems on the side of a house. So otherwise, it's structurally the same, even though it's just a different type. Even though the setup is slightly different. So in this case, so what we're going to do is we're going to denote the length of this side by x, and then so is this side, and then this side we're going to denote by y. So the thing is that assuming that the fencing material costs $56 per foot, what is the least amount of money needed to build a fence? So the problem says, all right, part B essentially means we got to figure out the minimum cost. So minimize cost of fencing. So the thing is that now that we actually have an actual cost, now we actually do have to put up with the cost in this case. So in this case, it's not going to be like last time where we could just focus on the dimensions and essentially focus on the surface area or whatever what we're focusing on. So the thing is that now we actually do have to deal with the cost. So in this case, I'm going to denote with C sub t for total. So C sub t says, all right, so in this case, the total cost is going to be the product of 2 things. It's going to be the cost per foot of fencing times the actual amount of fencing we have. So amount of fencing. So the thing is that the problem explicitly gives us what the cost per foot of fencing is as $56 per foot. So that part's pretty nice and clean, but then what about the actual amount of fencing we have? So taking a look at the variables we are given here, what is the amount of fencing that we have in feet?
Would it be 2x plus 1?
Yeah, just 2x plus 1, right? So in this case, the cost per foot, this is cost per foot of fencing, 56, and then the amount of fencing is 2x plus 1. Okay? So that takes care of that. So one thing to note here is that, let's take a look at the units first of all before we move on. So 56, this is in dollars per foot, and then 2x plus y, as we already established, is in feet. So as a result, then the total cost says, all right, we essentially multiply these 2 units together to essentially get that the total cost is in dollars, essentially. Okay. So that takes care of that part. And when we can see that as sort of the units here essentially sort of cancel out. So that's when we could see that this ultimately ends up being in dollars. Okay, so that takes care of part B. So now part C says, all right, well, we still have everything in terms of two variables, so we got to fix that. So what's our constraint? Well, our area is given as 640,000 square feet. So in terms of the variables that we're given, that means that 640,000 can be expressed as the product of what two things?
X times 1.
6 times 1, right? Okay. And then again, you can solve for either one of these to get to the final answer. But just to be consistent with the thing I have in my notes, let's go ahead and solve for y here. So y equals 640,000 over x. So that's part C. Part D says, all right, now that we have y in terms of x, let's go ahead and plug this into part B's results. So C equals 56 times 2x plus 6,400,000 over x. So then if we multiply 56 to both terms here via distributive property, then what we get is, well, 112x plus 35,840,000 over x. So then this becomes our objective function, which represents the cost in terms of one variable x. Okay? So this is our objective function. So then part E says, all right, well, just go ahead and differentiate, solve, set it equal to 0 and solve. So first let's go ahead and differentiate this to see what happens. So what are you guys going to use your derivative? Go ahead.
112 minus that number over x squared.
Good answer. That number, yes, I like that. Then that number over x squared, that's correct. So set it equal to 0, let's see what happens. So the thing is that now we have an x squared hanging out here. So in this case, if we first solve for x squared here, what should we end up with regarding what x squared equals in solving from here? Go ahead.
X squared equals 320,000.
Just 300? Oh, yeah. So then, yeah, because what happens is that if you solve for x squared, you have 35,840,000 over 112, which, when you plug into a calculator, yields you 320,000. Right. Okay. So then from there, we say, all right, well, go ahead and square both sides to get the value of x. That will give us the necessary minimum cost. So we have x equals the square root of 320,000. No, sorry, 320. Yeah, 320,000. Yep. Okay, so from here, we say, all right, well, let's go ahead and plug this into our minimum cost because that's ultimately what we need here. So then C of the square root of 320,000 So if we plug this into a calculator and round to 2 decimal places, then what should we end up with as our final answer? Plug this into a calculator. Go ahead.
I got 126, 713,535.
Yep. Point, what was it?
535.
So 0.54, right?
Yeah.
Yeah. Okay. So that would be your minimum cost here. Okay. Okay. So that's example 1. So any questions on that part? Okay. Does anyone still need this? Okay. So moving on to example 2. So the premise is that Steve would like to construct a box with volume 55 cubic feet using only bedrock and obsidian. So the bedrock costs 13 emeralds per square foot, and the obsidian costs 6 emeralds per square foot. If the obsidian goes on the sides and the bedrock on the top and bottom, and if the length of the base is to be 3 times the width of the base, find the dimensions of the box that will minimize the cost of construction. And then round to 2 decimal places. So moving on to step A says, all right, well, we have another box we have to put up with. So here's our good old box. Now in this case, the problem actually wants us to include the top part as well. So our box with top. Okay, so in this case now, here's what things are a bit different. So we don't have a square base, so now we have to be a bit careful. So we have L, W, and H are going to be our assumed dimensions here. So in this case, let's go ahead and work from that. So part B says, all right, if we take a look at the problem, we again have to minimize the cost of constructing the box. So that's, okay, that's part B. So minimize costs of, in this case, the box. Okay? So in this case, if we take a sort of a page from what we did from last time, let's say, all right, well, if we denote C as the total cost of the box, then because the different parts of the box are made out of different materials, we have to break it up accordingly. So in this case, the top and bottom is made of obsidian and, top and bottom is made of bedrock, and obsidian is on the sides. Okay? So in this case, we have to break this up accordingly. So we have the top plus bottom. Okay? So the cost of those parts, and then plus the cost of the sides. Okay? So if we take a page from what we did in the, take a page from what we did from the last example, we say, all right, well, if we focus on the cost of the top and bottom, what would be the product here?
What top and bottom be length and width?
Well, careful. Remember, we have to focus on the cost of the top and bottom. So taking a page from what we did in example 1. top and bottom costs is going to end up costing us 13 emeralds per square foot, right? So we're going to have to multiply first by what?
13.
13, and then in this case, and then times what? Times the area of the top and bottom, right? Area top and bottom. Okay. Then, so if we do the similar thing with the sides, then what product should we end up with that looks something like this?
Maybe 6 times area of the side.
Good. Yep, 6 times area of the sides. Okay. So the thing is that now the area of the top and bottom, the total area of the top and bottom, is then going to end up being what? So what you notice is that the top and bottom both have dimensions length and width. So since we have 2 such faces with those dimensions, that means the area of the top and bottom will be what? We have 2 faces of dimensions L and W. So what is their total area going to be?
Maybe 2 plus LW?
Now it's not 2 plus LW.
Or 2 times LW?
2 times LW, right? Okay. And then do a similar thing with the sides. So in this case, for the sides, we have 2 faces with dimensions W and H, and then we have 2 sides with dimensions L and H. So in a similar fashion, we'll have 2LH plus 2WH is going to end up being the total area of the sides. Okay. So now if we distribute all these constants into all our terms, we end up with 26 LW plus 12 LH plus 12 WH. Okay. So that part's not too bad. So this gives us our cost in terms of each dimension. But, well, this is an optimization problem, and, well, we kind of need everything in terms of one variable. So, how do we fix that? Well, let's look at our constraints. So, one thing we haven't used yet that could be useful is the problem states that the length of the base is 3 times the width of the base. So L is the length of our base, and W is the width. So using this part here gives us one of our constraints as what? So the length is equal to 3 times the width. So actually I kind of just basically said it. So in this case, that means L equals 3 times W, essentially is what that means. So in that case, that says, all right, well, that's one constraint. Then 55, or actually, before we move on to that, well, one thing we notice is that we also have the volume is supposed to be 55 cubic feet. So 55 says, all right, well, that's the volume of the box, so correspondingly that should be the length of the product of our dimensions. But thankfully, we have that one of the dimensions is in terms of another one. So we can write this a bit further as 3W squared times H. So then, setting this equal to 55 says that, all right, well, focusing on this equation here, which variable do you think we should solve for? To make our lives a bit easier here. We should probably solve for H, right? So then if we divide both sides by 3W squared, we should end up with 55 over 3W squared. Okay? So that gives us that the length and the height are now both in terms of W. So now let's go ahead and plug this back into our cost function as step D. So we have C equals 26 times, well, in this case, L, which is 3W, times W. Then plus 12 times L, which is 3W, times h, which is 55 over 3w squared. So 3w squared. And then plus 12 times w times h, which is 55 over 3w squared. So now let's go ahead and clean this up a bit. So this first term is just, well, 26 times 3 is 78. You plug that into a calculator. And then we have w squared. Then what do you notice about the next two terms? So the next two terms, for this second one, we have that there's a 3 on the top and bottom, so we can cancel those out. So then w, and then we also have a factor of w on top and bottom as well. So there's that. So then after that, we have 12 times 55. If you plug that into a calculator, we have that this is just 660. 12 times 55. So then ultimately, we have 660 over w is the second term. So then a similar thing for the third term says, all right, well, we have a factor of w on top and bottom that we can cancel out. So then if we plug, then we have 12 times 55 divided by 3, then what should that give us? So like I said, 12 times 55 is 660. So then dividing by that by 3 should net us what? 220. Good. 220 over w. So then put everything together, we end up with 78w squared plus 880 over w. So then we ultimately now have the objective function, the cost, in terms of w, one variable. Okay? So now let's go ahead and differentiate this bad boy. So c prime of w, applying power rules should give us what? Go ahead.
156w minus 880 over w squared.
Okay. So we have 156w minus 880 over w squared. So if we set this equal to 0 and solve for w, well, similar algebra as in the last example should be able to give us that we should end up having to solve for w cubed in this case. So if we do that, we say, all right, well, if we solve for w cubed in this equation here, what should we get from that? What fraction?
They're setting 156w minus 880 over w squared equal to w cubed.
No. I'm saying this equal to 0 and then saying solve for w cubed. Go ahead.
What is it, the base of
880 over 156. Good. Okay. So then as a result, well then if you take the cube root of both sides, we have the cube root of 880 over 156. So if you plug this into a calculator and run to 2 decimal places, what you'll notice is that this is approximately 1.78. So there's that part. So you might be thinking, well, why did I do that? Don't we need to deal with the exact value? Well, look back at what the question's asking us to do. It says, we got to find the dimensions of the box that minimize the cost. So in this case, we don't need the minimum cost as the final answer. We just need the dimensions that give us the minimum cost. So need dimensions. Oh, move this up a bit, my bad. So in this case, well, the good news is that we already have the other two dimensions, L and H, in terms of W, based on our constraints in step C. So let's go ahead and take this exact value of W here and plug them into our two constraints. So if we have L equals 3 times W, which is cube root of 880 over 156, that's just approximately 5.34. And H, meanwhile, is just 55 over 3 times the cube root of 880 over 156 squared. So plug that into a calculator, you should end up with 5.79. Okay, so those are our dimensions that minimize the cost. So W is approximately 1.78, L is approximately 5.34, and H is approximately 5.79. Okay, so that's example 2. So any questions on that before we move on to example 3?
Quick question for, in part C, where you try to get the constraint, where did you get the 3W squared H from? Like the...
Because we already have L is equal to 3W.
Oh yeah, and then the other W.
Yep. Okay, so that's example 2. Okay, so now example 3. So this one's going to be a little bit quicker in terms of applications. So the thing is that Dunder Mifflin's marketing department has determined that if paper is sold at the price of P dollars per ream, where ream is basically those units of paper that you see at Walmart, for instance, they can sell Q equals 1600 minus 100 P reams, which are units of paper, and each unit costs $4 to make. So step 1 says, how much should Dunder Mifflin charge to maximize their revenue? So in this case, the problem makes it pretty clear what we got to maximize. So let's go ahead and move on from this. So for 1, the thing is that there's not really a picture we have to deal with here, so we kind of just can skip this step. So skip that. Part B, meanwhile, says, okay, maximize revenue, as we just established. But, well, what is revenue? Well, revenue is just, well, the price per ream times the number of units sold. So in this case, thankfully, the problem gives us those two quantities here. So the thing is that the price is given as P dollars per ream. So this just becomes P. And the units sold, meanwhile, they say they can sell Q reams, which are units of paper, if we charge at P dollars per ream. So in that case, that units sold end up corresponding to P times, and the units sold ends up corresponding to Q here. So this is going to be our revenue. So that's step B, essentially. Now, the good news is that our constraints, well, that's actually given in the problem for us, because, so our constraints, so constraint says Q can be expressed in terms of P as 1600 minus 100P. So Q equals 1600 minus 100 times P. So that's that part, and then part D says, all right, well, go ahead and take this constraint, plug it into here, so that we have revenue in terms of P. So then RP becomes P times 1600 minus 100 times P, or if you prefer, 1600 P minus 100 P squared. So then if we solve for, so then if we differentiate and set equal to 0 and solve, what is the value of P that we end up with as our final answer here? Go ahead.
800.
P equals 800. Okay. So first off, let's take a step back. What's the derivative?
It'll be 1600 minus 200p.
Yep, 1600 minus 200p. So if we set that equal to 0 and solve for p, we should end up with that is equal to what? Yeah, that's what we need, 8. Okay? And the good news is that the problem says how much should Dunder Mifflin charge? Well, that directly corresponds to P, so the only thing we care about is P. Okay, that was the worst data I've ever written in my life. Like, seriously though. Okay, let me fix that. That's much better. Okay, so P equals 8 is ultimately the answer we need here. Okay? So, with that mentality in mind, let's go ahead and briefly go through step 2, our part here. Because now in this case, now we got to maximize the profit. Okay? So, as before, step A, there's no picture, so skip this. Not applicable. So part B says we got to maximize the profit. Now the profit, meanwhile, is price per ream minus cost per ream. So, and then times the number of units sold. So as before, the unit sold is still Q, so nothing changes there. But price per ream is still P as before. But now each unit costs $4 to make, so what does that say about what changes here? So what would go inside here based on what we have as our definition of profit here? So P is the price per ream, right? And the cost per ream says it's that cost per ream is $4 is 4. So what should I tell you about what goes inside here?
It'll be 4p. Or I mean p minus 4.
Yeah, P minus 4. Yeah. Okay. So that's going to be our profit. And then part C, constraint as before, is still Q equals 1600 minus 100p. So then part D is just, well, our function f of p, which is going to be our profit function, is then p minus 4 times 1600 minus 100 times p. Okay? So now in this case, what you'll probably want to do is you'll probably want to FOIL this out to make the derivative computations a bit easier. But all I'm going to say for now is, in this case, once you FOIL this out and differentiate, set it equal to 0, and solve, then I'll just tell you what the final answer should be. Well, once I pull my paper up, because we're running along paper. So, whoops. So the final answer you should get is p equals 10. So once you FOIL this out, and then do step E from that, you should end up with p equals 10 as your final answer. So I'll just say, okay, well, if you FOIL this out, do the same thing that we did before, that should be your final answer. You can check the web page, or you can briefly check on your own when you get a chance. Okay? So that's basically example 3 in a nutshell. So any questions on any of that before we move on to our last example? So our last example is a bit more unique in regards to what we've been doing up until this point, because now we're actually dealing with stuff in the xy plane. So, because example 4 says we have to find the points on the curve y equals x squared plus 1 closest to the point 0, comma 4, and round to the nearest 2 decimal places. So, here's where things are a bit more interesting, because before we had usually some nice geometry like a box or a rectangular fence or whatever. But now we're back on the xy plane. So here we say, all right, well, we have x here, we got y here. So if you remember, x squared plus 1, what the graph of that looks like is just your usual parabola x squared, but because of the plus 1, you have to shift the entire graph up 1 unit. So ultimately, your graph is going to look something like this. Okay? So got tick 1, then 2, 3, 4. So we have to figure out, all right, if y equals x squared is this graph, or x squared plus 1, that's our graph, and then it's closest to the point 0, comma 4. So we got to say, all right, well, which of the points on this curve is closest to 0, comma 4? So we say, all right, well, if we focus on the distance between the parabola and our points, we say, all right, well, which of them has the smallest distance between the point and the curve? Okay? So what that tells us is that, all right, well, we have to work with essentially the distance formula, essentially. So part B says, all right, well, so before we work from that, well, do you guys remember the distance formula from high school? Just out of sheer curiosity. Okay, I'm just going to take that as a no, so, which is fine. We haven't really used it in this class yet, so it's okay if you guys don't remember it, but off the top of your heads, but in this case, the distance formula is the square root of x minus x naught squared plus y minus y naught squared. So hopefully hopefully that should at least look familiar. So we say, all right, well, based on what I explained in part A, that means we got to figure out, all right, we got to figure out some way to minimize the distance d here. So minimize d. Okay? So that's ultimately our goal in this problem. Now, one thing that might help it with derivative computations, though, is that we can actually make things a bit easier if we actually consider the square of this distance. So namely, we focus on capital D as little d squared, as x minus x naught squared plus y minus y naught squared. Then it suffices to focus on this right here to minimize derivative computations. Because what you'll notice is that the thing is that because of the way we're focusing on the problem here, any distance here is always going to be non-zero because x squared plus 1 is not a point, does not have 0, comma 4 as a point on its curve. So that's one thing to note here. So that way you can focus on this distance here as something non-zero. And further, big D and little d will have the same critical points, so we can focus on this representation of our distance to make our lives a bit easier here. So suffices to minimize capital D to simplify derivative computations. Okay? Because like I said, big D and little d have same critical points. Okay? So that's essentially part D. So now we say, all right, well, it's good we have this sort of constraint formula now, or a constraint function, but now we got to get this in terms of one variable. So how do we do that? Well, the good news is that the way I set up our distance formula is to say, all right, I'm going to let x naught, y naught represent the point that we're given, and I'm going to let x comma y be corresponding to our curve here. So points is x naught, y naught is 0, 4. And any points on curve is of the form. So x comma y equals, well, y is equal to x squared plus 1. So we have x comma x squared plus 1. So what that tells us is that the reason why I did this is so we can say, all right, so we have x naught and y naught are two given constants, and y can be expressed in terms of x in this way. So what that means is that now, moving on to d, we can plug all those into here to get the capital D in terms of x. So we have d equals x minus 0 quantity squared minus, well, y equals x squared plus 1, and then minus y naught, which is 4. Square that. So what you notice is that, well, x minus 0 quantity squared, that just simplifies pretty nicely to x squared. And then this part here just simplifies to x squared minus 3 inside the parentheses, and then quantity squared. Okay. So in this case, this becomes our distance, or our objective function in terms of x. Okay? So what you notice from this is that, all right, well, now let's go ahead and do our usual set derivative equal to 0 and solve. So first off, what's our derivative? Well, this first term, as you guys should hopefully be able to see by now, is 2x. But what's the derivative of this guy? Do you guys remember how to handle that guy? Right, because remember, chain rule is still a thing. So this is how you get the derivative of this follows from chain rule. Okay? Because remember, this part here will correspond to the 2 times x squared minus 3. That simply corresponds to the sort of the derivative of the outer function composed with the inner function, this part here, and then this part here is the derivative of our inner function. So the outer function, so outer is equal to x squared, and then inner is x squared minus 3. So that's one way you could see the application of chain rule in this case. Okay? So now let's go ahead and put everything together. So we have 2x plus, well, let's see. One way you could compress this down a tiny bit is that we have 2 times 2x, so 4x times x squared minus 3. So let's see. So if we distribute 4x into both terms here, we have 2x plus 4x cubed minus 12x, okay, which then just equals, well, after a bit of simplification, minus 4x cubed minus 10x. So if we set this bad boy equal to 0, we should end up with 3 values of x that give us zeros here. So what values of x would those be? Go ahead.
I got x equals 0 and x equals square root and plus or minus square root of 5.
Right. Because what you notice is that you can factor out 2x from both terms here to get 2x times 2x squared minus 5 equals 0. And then in this case, because of the geometry, x can be any real number at once. So in this case, x equals 0 and plus or minus the square root of 5 halves. well, hold on a minute. That means we have 3 values of x here, which is definitely different than what we've been doing up until this point. So in this case, now we got to figure out, all right, well, which of these give us the necessary minimum here? Well, that's where the second derivative test comes into play. So use second derivative test to see which ones give max/minimum. Okay, so we say, all right, well, first off, what's the second derivative in order to be able to apply the second derivative test? Well, so the good news is that with the second derivative, well, all we really have to do is just take the derivative of d prime to get the second derivative. So the good news is that d prime of x can be expressed as 4x cubed minus 10x. So if we take the power rule of this, well, that's just 12x squared minus 10. So in this case, we say, all right, well, if we let x equal 0, well, that's going to give us pretty clearly a negative second derivative. So x equals 0. So the second derivative of d at 0 is going to be negative 10, which is clearly less than 0. So in this case, if you remember from the second derivative test, what does that tell you about the type of extrema that is at x equals 0? So in this case, remember, the second derivative being negative corresponds to a concave down function, right? So what kind of extrema do we get there? Maximum, right. Okay. So that's that part. So it definitely seems like x equals 0 is out of the consideration here. So let's focus on the other two. So we have x equals plus or minus the square root of 5 halves. So if we plug in either of those 2 points into our second derivative, well, that tells us what? So if we square if we square plus or minus the square root of 5 halves, what should we get as our results? If we square this part here. You just get 5 halves, right? Okay. And then minus 10. So would this be positive or negative? Be positive, right? So that would tell us that we get, by second derivative test, that should pretty quickly tell you that we're going to get a minimum here. Because the second derivative is positive, and hence we have a concave up function at that point. So, actually, sorry, this is not step F yet. This is, well, in this case, now we have step F. So that means the points on the curve, x comma x squared plus 1, are going to be positive 5 square root of 5 halves, and then comma, well, we have to find the corresponding y-coordinate. So then what we notice is that this is just, we plug this back into our x squared plus 1 constraint. So if we take the square of this value here, then what we get is, as we established, this is just 5 halves plus 1, which is 7 halves. So that means our y-coordinate is going to be 7 halves for both points. So we have positive square root of 5 halves, comma 7 halves, and then negative square root of 5 halves, 7 halves. Okay, and that's example 4.